Tonight, we're going to explore something terrifying. Imagine a beam of energy so powerful that it could alter the chemistry of an entire planet's atmosphere, from hundreds or even thousands of light years away. No impact, no explosion on the surface, no warning whatsoever. Just a silent flash of radiation lasting a few seconds. And within hours, the planet begins to die. Not because anything touched it, but because its atmosphere was rewritten at the molecular level. This is what a gamma-ray burst could do to a world like ours. And the most unsettling part isn't the destruction itself, it's the fact that we wouldn't see it coming, we wouldn't feel it arrive, and by the time we noticed anything was wrong, the damage would already be done. Before we go any further, if you find this kind of deep exploration interesting, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. Let's start with something you already understand. Light. You see it every day. You flip a switch and a bulb illuminates a room. You walk outside and the sun warms your face. Light seems simple, ordinary, harmless, but light is actually a form of energy. It's electromagnetic radiation, waves of electric and magnetic fields rippling through space at about 300,000 kilometers per second. And here's what most people don't think about. The light you see with your eyes, the visible spectrum of reds and oranges and yellows and greens and blues and violets, that's only a tiny sliver of the full electromagnetic spectrum. A very tiny sliver. There are forms of light you can't see at all. Some of them are lower in energy than visible light. Radio waves, for instance. They carry the signals that bring music to your car stereo and data to your phone. Microwaves heat your food. Infrared radiation is what you feel as warmth when you hold your hands near a fire. These are all forms of light, just with longer wavelengths and lower energy than what your eyes can detect. Then, there are forms of light with higher energy than visible light. Ultraviolet radiation is what gives you a sunburn. It carries enough energy to damage the DNA in your skin cells, which is why your body responds with inflammation and redness. X-rays carry even more energy. They can pass through soft tissue and reveal your bones on a medical scan. They carry enough energy to penetrate matter that visible light cannot. But beyond ultraviolet, beyond X-rays, there is one more category of light. The most energetic form of electromagnetic radiation in the universe. Gamma rays. Gamma rays are light, technically. They obey the same physics as the light from your desk lamp. They travel at the same speed. They're made of the same fundamental thing, photons. But a single gamma ray photon can carry millions or even billions of times more energy than a single photon of visible light. If visible light is a gentle tap on the shoulder, a gamma ray photon is a freight train. The wavelength of a gamma-ray photon is extraordinarily short, smaller than an atom. In fact, the most energetic gamma rays have wavelengths smaller than the nucleus of an atom. That's part of what makes them so penetrating and so destructive. They interact with matter at the subatomic scale, at the level of individual atomic nuclei and electrons. When gamma-ray photons hit matter, they don't just bounce off or get absorbed gently. They slam into atoms with so much energy that they rip electrons away from their nuclei. They shatter molecular bonds. They break apart the very structure of matter at the atomic level. This process is called ionization, and it's fundamentally destructive to the delicate chemistry that holds molecules together, especially the complex molecules that living things depend on. A gamma-ray photon can also produce pairs of particles when it interacts with matter. A sufficiently energetic gamma ray passing near an atomic nucleus can spontaneously create an electron and its antimatter counterpart, a positron, converting pure energy into matter, according to Einstein's famous equation E equals mc squared. The positron then quickly encounters a regular electron and both annihilate, producing more gamma rays. This cascade effect means that a single gamma ray photon can trigger a chain of secondary interactions, spreading its destructive energy through the material it passes through. We are going to come back to this idea later, because ionization is the key to understanding everything a gamma ray burst does to a planet. But first, you need to understand where these gamma rays come from and why a gamma ray burst is unlike anything else in the known universe. A gamma ray burst is exactly what the name suggests. It's a burst of gamma ray radiation, but calling it a burst makes it sound small, like a camera flash or a firecracker. It's not. A gamma ray burst is the single most energetic type of explosion that occurs in the universe. More powerful than a supernova. More energetic than the collision of galaxies. More violent than almost any other event that physics permits. When a gamma ray burst goes off, it releases an almost incomprehensible amount of energy in a very short period of time. We're talking about events that can release more energy in 10 seconds than our sun will produce over its entire 10 billion year lifetime. Let me say that again, because it deserves to sink in. In roughly 10 seconds, a gamma ray burst can outshine the entire energy output of a star that burns steadily for 10 billion years. That's not an exaggeration for dramatic effect. That's what the observations and the physics tell us. The first gamma ray bursts were detected in the late 1960s, completely by accident. The United States had launched a series of satellites called the Vela satellites. These weren't designed for astronomy. They were military satellites built to monitor the Nuclear Test Ban Treaty of 1963. Their job was to watch for the telltale gamma ray signatures of nuclear weapons being detonated in space or in Earth's atmosphere. The idea was that if the Soviet Union secretly tested a nuclear bomb, the Vela satellites would detect the burst of gamma radiation and alert the United States. But starting in 1967, the Vela satellites began picking up gamma ray flashes that didn't match any known nuclear weapon signature. These flashes were coming from deep space, not from Earth or from anything near Earth. They were brief, intense, and completely mysterious. For years, nobody knew what they were. The data was initially classified because it came from military satellites. It wasn't until 1973 that the discovery was published in a scientific paper. And even then, nobody had a good explanation. Astronomers debated for decades about what could produce such intense bursts of gamma radiation. Some thought they came from within our own galaxy. Others thought they might come from much farther away. The problem with the second idea was that if these bursts were coming from distant galaxies, then the amount of energy involved would be absurd. It would require an energy output that seemed physically impossible. It wasn't until the late 1990s, with better satellites and telescopes, that astronomers finally solved the mystery. The key breakthrough came from a satellite called Beppo-Sax, an Italian-Dutch X-ray astronomy satellite launched in 1996. Beppo-Sax could rapidly determine the position of a gamma ray burst on the sky with enough accuracy that ground-based telescopes could then point at that spot and search for an optical counterpart. In 1997, for the first time, astronomers detected the afterglow of a gamma-ray burst, the fading glow of radiation that lingers after the initial flash. This afterglow, visible in X-rays and then in optical light, allowed astronomers to pinpoint the exact location on the sky. And when they looked at that location with large ground-based telescopes, they found a faint galaxy. By measuring the redshift of that galaxy, they could determine its distance, and the answer was stunning. These bursts were coming from galaxies billions of light years away. The most distant gamma-ray burst ever detected occurred about 13 billion light years from Earth. That means the explosion happened when the universe was less than 1 billion years old, just a fraction of its current age. And despite being that incomprehensibly far away, the gamma-ray flash was still bright enough to be detected by our instruments. For a brief moment, some gamma-ray bursts outshine the entire observable universe in gamma-ray light. They become the brightest single objects in the sky, visible across billions of light years, brighter than 100 billion suns combined. One gamma-ray burst detected in 2008, designated GRB 080319b, was briefly visible to the naked eye from Earth, despite being 7.5 billion light-years away. An explosion so far away that its light had been traveling for more than half the age of the universe. And yet, for about 30 seconds, if you had been looking at the right patch of sky at the right moment, you could have seen it without a telescope. That's how powerful these events are. Now, here's the critical thing you need to understand. A gamma-ray burst is not a simple spherical explosion like a bomb going off and sending energy equally in all directions. This is a point that's often misunderstood, and it changes everything about how dangerous these events really are. A gamma-ray burst produces jets. When the explosion occurs, the energy doesn't radiate outward in a uniform sphere. Instead, it gets concentrated to two narrow beams of matter and radiation that shoot out in opposite directions from the source, like two incredibly powerful searchlights pointed in opposite directions. These jets are narrow. Astronomers estimate that the opening angle of a typical gamma-ray burst jet is only a few degrees. Some estimates put it at around 2 to 20 degrees, depending on the burst. Think of that compared to a full sphere, which covers 360 degrees in every direction. A jet that covers only a few degrees of sky is an incredibly small fraction of the total sphere. This means that the vast majority of the burst's energy is concentrated into a tiny cone of space. If you happen to be inside that cone, if the jet is aimed at you, you receive an enormous dose of energy. If you're outside the cone, you might not detect anything at all, or you detect only a much weaker, off-axis afterglow. This is why gamma-ray bursts appear so extraordinarily bright when we detect them. We're usually seeing them because the jet happens to be pointed in our general direction. We're seeing all that concentrated energy beamed right at us across billions of light years. If the energy was spread evenly across a sphere, the total energy output would be lower, still enormous, but lower. The jet structure is what makes gamma-ray bursts seem so impossibly luminous. It's also what makes them so dangerous to anything that happens to be in the path of the beam. The material in these jets moves at relativistic speeds. That means speeds very close to the speed of light. We're talking about matter moving at 99% or even 99.9% of the speed of light. At these speeds, the physics gets extreme. Time dilation, length contraction, all the bizarre effects predicted by Einstein's theory of special relativity come into play. The jet material is so energetic, so fast, so concentrated, that it generates gamma rays through a variety of physical processes as it plows through the surrounding space. The exact mechanisms are still being studied, but the leading models involve internal shocks within the jet, where faster moving material catches up to slower moving material and collides, converting kinetic energy into radiation. There are also external shocks, where the jet slams into the surrounding interstellar medium, the thin gas and dust between stars, generating additional radiation across many wavelengths. So what actually creates these jets in the first place? What kind of event produces such an extreme outpouring of energy? Astronomers have identified two main types of gamma ray bursts based on how long they last, and each type has a different origin. Long-duration gamma ray bursts last more than about 2 seconds. Most of them last between 10 and a few hundred seconds, though some have been observed lasting thousands of seconds. These are caused by the deaths of very massive stars, not just any star. We're talking about stars that are at least 20 to 30 times the mass of our Sun, and often much more. These are enormous, brilliant stars that burn through their nuclear fuel rapidly. A star like our Sun will burn steadily for about 10 billion years. A star 30 times more massive might exhaust its fuel in just a few million years. That's 1,000 times shorter. These massive stars live fast and die violently. While a star like our Sun burns steadily for billions of years, barely changing in appearance over the span of human civilization, a star 30 times more massive blazes through its nuclear fuel at a furious rate, shining millions of times brighter than the Sun, but lasting only a tiny fraction as long. When such a star runs out of fuel, its core collapses. Throughout its life, the star has been fighting a constant battle between two forces: gravity pulling everything inward, and radiation pressure from nuclear fusion pushing everything outward. As long as fusion continues in the core, the star is stable. These two forces balance each other. But when the fuel runs out, when there's nothing left to fuse, radiation pressure drops and gravity wins instantly. The core implodes in a fraction of a second. The outer layers of the star can no longer be supported against gravity, and the inner core collapses at speeds reaching a quarter of the speed of light, forming either a neutron star or, more commonly for the most massive stars, a black hole. As the core collapses and the black hole forms, an enormous amount of gravitational energy is released. Material that doesn't fall directly into the black hole swirls around it, forming a superheated accretion disk. Temperatures in this disk can reach billions of degrees. Magnetic fields become twisted and amplified to extraordinary strengths, and some of this energy gets channeled into those relativistic jets that punch through the outer layers of the dying star and blast outward into space. The whole process is sometimes called a collapser, because it involves the collapse of the stellar core. The jet has to bore its way out through the star's envelope, which can take several seconds. If the star is too large or the jet too weak, the jet might stall inside the star and never break through, producing a failed gamma ray burst. Only when the jet successfully punches through the stellar surface does the gamma ray burst become visible to the outside universe. The result is both a supernova, the explosive destruction of the outer layers of the star, and a gamma ray burst, the focused jet of energy that emerges from the core collapse. The supernova is impressive on its own. A typical supernova releases about 10 to the 44 joules of energy, which is about as much energy as the Sun will emit over its entire lifetime. But the gamma ray burst produced during the same event, because it's focused into narrow jets, can deliver an energy flux along the jet axis that far exceeds even the supernova itself. Short-duration gamma-ray bursts last less than about 2 seconds, often just a fraction of a second. These have a completely different origin. They're caused by the merger of two compact objects, typically two neutron stars, or a neutron star and a black hole. Neutron stars are the incredibly dense remnants of earlier supernova explosions. A neutron star packs roughly 1.5 times the mass of the Sun into a sphere only about 12 miles across. The density is staggering. A teaspoon of neutron star material would weigh about 4 billion tons on Earth. When two neutron stars orbit each other, they gradually lose energy through the emission of gravitational waves. Ripples in the fabric of space-time predicted by Einstein's general relativity and directly detected for the first time in 2015 by the LIGO Observatory. As they lose energy, the two neutron stars spiral closer and closer together. This process can take millions or even billions of years, but it's relentless. The orbit shrinks slowly, the neutron stars get closer, and eventually they merge in a catastrophic collision. The merger happens fast. In the final moments, the two neutron stars are orbiting each other hundreds of times per second, moving at a significant fraction of the speed of light. When they finally collide, the result is an explosion of extraordinary violence. A burst of gravitational waves is released, along with a flash of gamma-ray radiation lasting less than 2 seconds. Again, relativistic jets form from the merger site, producing the gamma-ray burst. The merger also creates and scatters heavy elements: gold, platinum, uranium, elements that are forged in the extreme conditions of the collision and flung outward into space. In fact, a significant fraction of the heavy elements in the universe, including the gold in jewelry and the uranium in nuclear reactors, was probably created in neutron star mergers. In 2017, astronomers observed both the gravitational waves and the electromagnetic radiation from a neutron star merger for the first time. The event was called GW170817, and it was detected about 130 million light-years away in a galaxy called NGC 4993. This was a landmark moment in astronomy. It confirmed that short gamma-ray bursts are indeed produced by neutron star mergers, a hypothesis that had been debated for decades. Now, let's talk about energy in terms that actually mean something. Because when scientists say a gamma-ray burst releases 10 to the 47 joules of energy in its jets, that number doesn't connect to anything in everyday experience. So let me try to build a sense of scale that makes the power of these events feel real. The Sun emits about 3.8 times 10 to the 26 watts of power. That's the total energy output every second. It's an enormous number by human standards. The Sun is a nuclear furnace converting about 600 million tons of hydrogen into helium every second. The energy it releases in 1 second could power all of human civilization for roughly 500,000 years at current energy consumption rates. That's in 1 second. Now, the Sun will keep doing this for another 5 billion years or so, producing a total lifetime energy output of roughly 10 to the 44 joules. That's the total energy the Sun will ever produce from its birth to its death. A single long-duration gamma-ray burst can release between 10 to the 44 and 10 to the 47 joules in its jets in a matter of seconds. The lower end of that range equals the sun's entire lifetime output. The upper end is 1,000 times more than that. And this energy is released not over billions of years, but in 10 or 20 or maybe 100 seconds. The power output during those few seconds is almost beyond language. There's no human experience that provides a meaningful comparison. All the nuclear weapons ever built by humanity, every warhead in every arsenal of every nation in history, if you detonated them all simultaneously, the total energy released would be roughly 10 to the 19 joules. A gamma ray burst releases 10 to the 47 joules. That's 10 to the 28th times more energy. That's 10 billion times more energy than every nuclear weapon ever created. And all of it compressed into a few seconds, focused into a narrow beam. To make this even more vivid, consider the asteroid impact that wiped out the dinosaurs 66 million years ago. That impact released roughly 10 to the 24 joules of energy, enough to trigger a global extinction event that killed about 75% of all species on Earth. A powerful gamma ray burst releases 10 to the 23 times more energy than that. That's 100 billion trillion times more energy than the impact that ended the age of the dinosaurs. And unlike an asteroid, which delivers its energy to a single point on a planet's surface, a gamma ray burst delivers its energy as radiation that can cross interstellar distances and arrive at a planet traveling at the speed of light. When astronomers first calculated these energies, many of them didn't believe the numbers. The figures seemed too extreme, too far beyond anything else in astrophysics. That's actually one of the reasons it took so long to accept that gamma ray bursts were coming from cosmological distances, from billions of light years away. If they were that far away, the energies had to be enormous. And for years, the numbers just seemed impossible. It wasn't until the jet model was developed that things start to make more sense. Because if you assume the energy is beamed into narrow jets rather than radiated uniformly across a sphere, the total energy budget drops significantly. Instead of needing 10 to the 54 joules, which would be the case for a perfectly spherical explosion visible at cosmological distances, you only need 10 to the 44 to 10 to the 47 joules. Still enormous, but physically plausible. The jet model solved the energy crisis and also explained why we don't see gamma ray bursts from every dying massive star. We only see the ones whose jets happen to be aimed at us. For every gamma ray burst we detect, there are probably hundreds that went off in other directions, with their jets pointing into empty space or at some other part of the universe completely invisible to us. The rate at which gamma ray bursts occur is another thing worth understanding. In the observable universe, astronomers detect roughly 1 gamma ray burst per day on average. That might sound frequent, but remember, the observable universe contains about 2 trillion galaxies. So 1 per day across 2 trillion galaxies means that in any individual galaxy, gamma ray bursts are rare events. In a galaxy like the Milky Way, the estimated rate is roughly 1 every few 100,000 to 1 million years for long-duration bursts. Short-duration bursts from neutron star mergers might be somewhat more frequent, but they also tend to be less energetic. So gamma ray bursts are not common events on a human timescale. You could live 1,000 human lifetimes and never experience one in your galaxy. But on a geological timescale, over the hundreds of millions and billions of years across which life evolves and planets exist, they become statistically significant. Earth is about 4.5 billion years old. Over that span of time, there have likely been several gamma-ray bursts within the Milky Way, whose jets pointed somewhere in our general direction. Given enough time, the odds of a gamma-ray burst affecting a planet in a given galaxy go from negligible to plausible to, over very long periods, almost certain. And the burst doesn't need to happen nearby to be dangerous. Because the energy is focused into narrow jets, a gamma-ray burst can deliver a significant radiation dose to a planet that is hundreds or even thousands of light years away from the source. The beam doesn't spread out nearly as quickly as a spherical explosion would, which means it retains its destructive potential over enormous distances. Here is another thing you should know. Not all gamma-ray bursts are equally powerful. They exist on a spectrum. Some are relatively modest, releasing energy at the lower end of the scale. Others are true monsters. In October of 2022, astronomers detected a gamma-ray burst designated GRB 221009A. It was nicknamed the Boat, standing for brightest of all time. And it earned that name. This burst was so intense that it temporarily overwhelmed the detectors on multiple satellites. It saturated instruments that were designed to handle extremely bright events. The burst came from a galaxy about 2.4 billion light years away, and its energy output was estimated to be among the highest ever recorded. The gamma-ray flux that reached Earth was powerful enough to measurably disturb Earth's ionosphere, the layer of charged particles in our upper atmosphere. A gamma-ray burst 2.4 billion light years away actually affected our planet's atmosphere in a detectable way. Not enough to cause any harm, not remotely close to dangerous levels, but enough that instruments could measure the disturbance. Now think about what would happen if that same burst had occurred not 2.4 billion light years away, but a few hundred light years away, or a few dozen, or closer. That's the question we're going to answer. Because the physics of gamma-ray bursts isn't just an abstract curiosity for astronomers studying distant explosions in faraway galaxies. It has real implications for any planet with an atmosphere, with liquid water, with life. The universe produces events of almost inconceivable violence, events that concentrate energy into narrow beams that can cross vast distances and still carry enough power to reshape a planet's atmosphere and threaten its biosphere. And the mechanism of that destruction is subtle. It's not fire. It's not an impact. It's not a shockwave that you'd see coming or feel arriving. It's radiation, invisible, silent, traveling at the speed of light. By the time it arrives, there's no time to react, no way to shield against it, no warning at all. There is no advanced signal that outruns the burst. The gamma rays are the first thing to arrive, because nothing travels faster than light. The beam crosses the distance at 300,000 kilometers per second, and it brings with it the energy to rewrite the chemistry of an entire world. What happens next? What that radiation actually does when it slams into a planetary atmosphere at the speed of light is where the story gets truly frightening. So now you understand what a gamma-ray burst is. You understand the scale of energy involved, the focused jets, the relativistic speeds. You understand that these are the most powerful explosions in the known universe, and that the energy they release in a few seconds can exceed what our sun will produce in its entire lifetime. You understand that the jets are narrow, concentrated, and that a planet in the path of one of these jets would receive an enormous dose of radiation with no advance warning. But all of that is just the setup. The real question is this: what happens when the energy actually arrives at a planet? What does a focus beam of a gamma radiation do when it slams into an atmosphere at the speed of light? And the answer is both more subtle and more devastating than most people expect. Because a gamma ray burst doesn't destroy a planet the way a bomb destroys a building. It doesn't blow things apart or set things on fire or create a crater. What it does is far more insidious. It poisons the atmosphere from the inside out. Let's walk through this step by step, starting with the moment the gamma rays arrive. The burst has happened somewhere in the galaxy, maybe a few hundred light years away, maybe a few thousand. A massive star has collapsed, or two neutron stars have merged, and a jet of relativistic material has produced an intense beam of gamma radiation aimed, by sheer cosmic chance, at a planet. The gamma rays cross the intervening space at the speed of light and slam into the atmosphere, without ceremony. One moment, the planet is spinning on its axis, its atmosphere functioning as it always has, its life forms going about their business. The sky looks normal. The air feels normal. Nothing about this moment distinguishes it from any other in the planet's history. And then, between one heartbeat and the next, the gamma ray photons begin pouring into the upper atmosphere. The assault has begun, and nothing on the surface has any way of knowing. The first thing that happens is that the gamma ray photons begin interacting with the upper atmosphere. Now, to understand what this means, you need to understand what an atmosphere actually is at the molecular level. An atmosphere isn't just empty air, it's a sea of molecules. Trillions upon trillions upon trillions of individual molecules, all bouncing around, colliding with each other, held in place by the planet's gravity. Earth's atmosphere, for example, is roughly 78% molecular nitrogen, 2 molecules of nitrogen bonded together, and about 21% molecular oxygen, 2 atoms of oxygen bonded together. The remaining 1% is mostly argon, with trace amounts of carbon dioxide, water vapor, neon, and other gases. The total mass of Earth's atmosphere is staggering, about 5.15 times 10 to the 18 kilograms. That's more than 5 million trillion kilograms of gas, stacked in a column above every square meter of the planet's surface, extending up to the edge of space. Most of this mass is concentrated in the lower atmosphere, the troposphere, where weather happens and where we live. But the critical interactions with a gamma ray burst happen higher up, in the stratosphere and above, where the air is thinner, but where the ozone layer resides. These molecules are held together by chemical bonds. The 2 nitrogen atoms in a nitrogen molecule share electrons in a strong triple bond. The 2 oxygen atoms in an oxygen molecule share electrons in a double bond. These bonds represent a specific amount of energy. If you put in enough energy to break those bonds, the molecules fall apart into individual atoms. And that's exactly what gamma ray photons do. When a gamma ray photon enters the atmosphere and encounters a molecule of nitrogen or oxygen, it doesn't gently push the molecule aside. It hits with so much energy that it ionizes the molecule, meaning it strips 1 or more electrons away from the atoms. This is not a small amount of energy. A typical gamma ray photon from a gamma ray burst carries millions of electron volts of energy. For comparison, the energy needed to ionize a nitrogen molecule to strip away one of its electrons is about 15.6 electron volts. The gamma ray photon carries millions of times more energy than is needed to ionize a single molecule. So each gamma ray photon doesn't just ionize one molecule, it triggers a cascade. The initial photon ionizes a molecule and in the process produces high energy secondary electrons. sometimes called photoelectrons. These electrons are moving fast, carrying a significant portion of the original photon's energy, and they behave almost like tiny bullets tearing through the surrounding gas. They fly through the atmosphere, and as they go, they ionize more molecules. Each of those newly freed electrons can ionize still more molecules. The process branches and branches again, like a tree growing from a single trunk into hundreds of twigs. One gamma-ray photon can ultimately ionize thousands of molecules through this cascading process. And remember, the burst doesn't deliver just one photon. It delivers an incomprehensibly large number of photons, all arriving in the span of seconds. The atmosphere lights up with ionization like a chain reaction, spreading outward from each point where a gamma-ray photon was absorbed. Now, here is where the chemistry gets critical. When you ionize and break apart nitrogen and oxygen molecules in an atmosphere, you don't just create a bunch of free atoms and electrons that float around harmlessly. You create reactive species, atoms and molecular fragments that are desperate to bond with something. Nitrogen atoms, freed from their usual pairing, will react with the abundant oxygen in the atmosphere. The result is a family of compounds called nitrogen oxides. Specifically, the key players are nitric oxide, which is one atom of nitrogen bonded to one atom of oxygen, and nitrogen dioxide, which is one atom of nitrogen bonded to two atoms of oxygen. These nitrogen oxides are the real weapon. They are the mechanism by which a gamma-ray burst does its lasting damage to a planet, because nitrogen oxides are extraordinarily efficient at destroying ozone. Ozone is a molecule made of three atoms of oxygen bonded together. It exists naturally in Earth's atmosphere, concentrated in a layer called the ozone layer, which sits in the stratosphere at an altitude of roughly 15 to 35 kilometers above the surface. The ozone layer is thin. If you compressed all the ozone in the atmosphere down to sea level, pressure and temperature, it would form a layer only about 3 millimeters thick. That's about the thickness of 2 pennies stacked on top of each other. It's almost nothing. And yet, this incredibly thin layer of ozone is one of the most important features of Earth's atmosphere. It absorbs the vast majority of the ultraviolet radiation coming from the sun, specifically the most biologically damaging wavelengths known as UVB and UVC radiation. Without the ozone layer, the sun's ultraviolet radiation would reach the surface at full intensity. UVB radiation damages DNA directly. It causes mutations in genetic material by breaking the chemical bonds that hold the DNA double helix together. It creates lesions in the genetic code, causing misreadings during cell replication that can lead to cancer or cell death. It kills cells. It's the reason you get sunburned, and it's a major cause of skin cancer in humans and animals. UVC radiation is even more energetic, and even more destructive to biological molecules. It disrupts proteins, destroys cell membranes, and can sterilize exposed surfaces of microorganisms within minutes. But under normal conditions, UVC is almost completely absorbed by the ozone layer and never reaches the ground. Life on Earth evolved under the assumption, so to speak, that the ozone layer would be there. The biological machinery of virtually every organism on the planet is calibrated to the current levels of ultraviolet radiation at the surface. Remove or significantly reduce the ozone layer, and that calibration breaks. The ozone layer is a planetary shield, an invisible barrier that makes the surface habitable for complex life. And nitrogen oxides tear it apart. The chemistry is straightforward and devastating. A single molecule of nitric oxide reacts with a molecule of ozone. The nitric oxide takes one of the ozone's 3 oxygen atoms, converting the ozone into ordinary molecular oxygen, which has only 2 atoms and provides no ultraviolet protection. The nitric oxide, having gained an oxygen atom, becomes nitrogen dioxide. But here's the crucial part. The nitrogen dioxide then reacts with another free oxygen atom, which are common in the stratosphere because ultraviolet light is constantly breaking oxygen molecules apart. This reaction converts the nitrogen dioxide back into nitric oxide, releasing the extra oxygen atom. The nitric oxide is regenerated. It's free to attack another ozone molecule, and another, and another. This is a catalytic cycle. The nitrogen oxide molecule is not consumed in the reaction. It acts as a catalyst, destroying ozone molecules one after another without being used up itself. A single molecule of nitric oxide can destroy thousands of ozone molecules before it's eventually removed from the stratosphere through other chemical processes. This means that even a relatively small increase in the concentration of nitrogen oxides in the stratosphere can result in a massive, disproportionate loss of ozone. Under normal conditions, there is a natural balance. Ozone is constantly being created in the stratosphere when ultraviolet light from the sun breaks apart oxygen molecules, and the resulting oxygen atoms recombine with other oxygen molecules to form ozone. Ozone is also constantly being destroyed by natural processes, including small amounts of naturally occurring nitrogen oxides. The creation and destruction rates are roughly equal, maintaining a stable ozone layer. But a gamma-ray burst shatters this balance. The flood of ionizing radiation pouring through the atmosphere creates an enormous surge of nitrogen oxides, far more than the natural processes can produce. The stratosphere is suddenly flooded with catalytic ozone destroyers, and they go to work immediately, chewing through the ozone layer at a rate that vastly exceeds the atmosphere's ability to replenish it. How much ozone would be destroyed? That depends on several factors, and we'll get to those shortly. But the models that scientists have run, detailed computer simulations of atmospheric chemistry under gamma-ray burst conditions, suggests that a sufficiently powerful burst at a close enough distance could deplete the ozone layer by 30%, 50%, or even 90% or more over the affected hemisphere. To put that in context, the human-caused ozone hole over Antarctica that alarmed the world in the 1980s and 1990s was a depletion of roughly 3 to 5% of global ozone and up to about 70% locally over Antarctica. That relatively modest depletion was enough to cause measurable increases in ultraviolet radiation at the surface and prompted an international treaty, the Montreal Protocol, to ban the chemicals responsible. A gamma-ray burst could make the Antarctic ozone hole look like a minor inconvenience by comparison. Now, there's an important detail here about geometry. A gamma-ray burst is a beam. It comes from a specific direction in the sky. This means it hits one hemisphere of the planet, the side facing the burst. The opposite hemisphere, the side facing away, is shielded by the bulk of the planet itself. The gamma rays don't curve around the planet. They travel in straight lines, just like visible light, just like any electromagnetic radiation. So the initial burst of ionizing radiation and the resulting surge of nitrogen oxides would be concentrated on one hemisphere. You might think that means the other half of the planet is safe. It's not. The atmosphere is not static. It moves constantly. Winds in the stratosphere, driven by temperature differences and the planet's rotation, circulate air around the globe. The stratosphere has its own circulation patterns, including large-scale movements called the Brewer-Dobson circulation that transport air from the tropics toward the poles. Within weeks to months, the nitrogen oxides created on the illuminated hemisphere would begin spreading to the opposite hemisphere through these circulation patterns, mixing into the global atmosphere. The ozone destruction would start as a hemispheric event, but would gradually become a global one. Within a few months, the entire planet's ozone layer would be significantly depleted, not just the side that was directly hit. This means that even the parts of the planet that were shielded from the initial gamma-ray flash would eventually suffer the consequences. There is no safe side. The atmosphere connects everything, and here's what makes this truly devastating. The ozone depletion doesn't end when the burst ends. The gamma-ray flash itself might last only 10 seconds, or 30 seconds, or a few minutes at most. But the nitrogen oxides it created persist in the stratosphere for years. These molecules don't just disappear when the radiation stops. They continue cycling through the catalytic destruction of ozone, molecule after molecule, for a long time. The atmospheric models suggest that significant ozone depletion could persist for 5 to 10 years after the burst, depending on the severity of the initial event. Some models suggest that for particularly powerful bursts at close range, measurable ozone depletion could last even longer. The atmosphere does eventually recover. Nitrogen oxides are slowly removed from the stratosphere through various chemical processes. They eventually get washed out by rain or react with other compounds in ways that neutralize them. And ozone production continues, slowly rebuilding the layer. But the recovery takes years, sometimes a decade or more. During that entire period, the planet's surface is exposed to elevated levels of ultraviolet radiation from its host star. The protective shield is weakened or gone, and the star's ultraviolet light pours through, reaching the surface at intensities that the planet's life forms have never experienced. But the ozone layer isn't the only atmospheric component affected. The massive ionization caused by the gamma-ray burst also affects the chemistry of the lower atmosphere in ways that can influence climate. One of the byproducts of the nitrogen oxide chemistry in the stratosphere is nitrogen dioxide, which is a brownish gas. In large enough concentrations, nitrogen dioxide can form a visible haze. This haze absorbs incoming visible light from the host star, reducing the amount of sunlight that reaches the surface. The effect is similar in principle to what happens after a large volcanic eruption, when sulfur dioxide injected into the stratosphere forms a haze that cools the planet by blocking sunlight. In the case of a gamma-ray burst, the nitrogen dioxide haze could reduce surface temperatures, potentially triggering a period of cooling that could last months or years. How much cooling would depend on how much nitrogen dioxide was produced, which in turn depends on the strength and proximity of the burst. Some models suggest surface cooling of a few degrees Celsius for a moderately close burst. A few degrees might not sound dramatic, but a global average cooling of just 3 to 5 degrees can have enormous effects. The last ice age had global average temperatures only about 5 to 6 degrees cooler than today, and it completely reshaped the planet's geography, with massive ice sheets covering large portions of North America and Europe. The irony is striking. The same event that strips away the planet's ultraviolet shield, allowing more harmful radiation to reach the surface, also creates a haze that blocks visible light and cools the planet. The surface gets simultaneously irradiated with more ultraviolet and starved of visible light and warmth. It's a double assault, one from the ultraviolet and one from the dimming of the star's warming light. But the important thing to understand is that the atmospheric effects of a gamma ray burst are not limited to the ozone layer. They ripple through the entire atmospheric system, altering chemistry, changing how light passes through the atmosphere, and potentially shifting the planet's climate. Now, let's talk about the factors that determine how severe all of this would be, because not every gamma ray burst would produce the same effects on a planet. The severity depends on several critical variables. The first and most obvious variable is distance. The intensity of radiation decreases with the square of the distance. This is a basic law of physics that applies to all forms of radiation spreading outward from a source. If you double the distance between the burst and the planet, the radiation intensity drops to 1/4. If you increase the distance by 10 times, the intensity drops to 1/100th. This inverse square law means that distance is an enormously powerful factor in determining outcomes. A gamma ray burst at 30 light years would deliver roughly 100 times more radiation per square meter than the same burst at 300 light years. The relationship is steep and unforgiving. The difference between a burst that causes minor ozone depletion and a burst that effectively destroys the ozone layer can come down to whether the event was 50 light years away or 500. At very close range, within about 30 light years or so for a powerful burst, the radiation dose could be catastrophic. At greater distances, say several thousand light years, even a powerful burst might produce only modest effects. Perhaps a few % reduction in ozone that the atmosphere could recover from relatively quickly. The second variable is the energy of the burst itself. As we discussed earlier, gamma ray bursts exist on a spectrum. Some are relatively modest, others are extraordinary. The total energy output, the duration of the burst, and the spectrum of the radiation all matter. A longer burst delivers more total energy. A burst with a harder spectrum, meaning a higher proportion of the most energetic gamma ray photons, penetrates deeper into the atmosphere and produces more ionization per photon. The boat event of 2022, for instance, was estimated to be an exceptionally rare burst, perhaps the most powerful in the last 10,000 years to reach Earth from any distance. Most bursts are considerably less energetic, but even a modest burst at close range can be devastating, and an exceptionally powerful burst can be dangerous at far greater distances than a typical one. The third variable is the angle of the jet. Gamma ray burst jets are not perfectly uniform across their width. The center of the jet, along its axis, is the most intense. The edges of the jet are less intense. If a planet happens to be directly along the jet axis, it receives the maximum possible radiation dose. If it's near the edge of the jet cone, it receives significantly less. A planet could be close to a gamma ray burst source, but because it sits at the edge of the jet rather than the center, receive a much lower dose than a planet farther away that happens to be directly on axis. The alignment matters enormously. A near miss, where the jet passes close to a planet but it doesn't hit it directly, might produce little to no effect. But a direct hit, where the jet axis points straight at the planet, delivers the full concentrated power of the burst. The fourth variable is the planet's own atmosphere. Not all atmospheres are equally vulnerable. The thickness and composition of the atmosphere determine how deeply the gamma rays penetrate and how much nitrogen oxide is produced. A planet with a thick, dense atmosphere has more material for the gamma rays to interact with. On one hand, This means more nitrogen oxides are produced. On the other hand, the thick atmosphere absorbs more of the radiation before it can reach the surface, providing some shielding. A planet with a thin atmosphere is more vulnerable in a different way. Less nitrogen oxide might be produced because there are fewer molecules to interact with. But the gamma rays can penetrate deeper, potentially reaching the lower atmosphere or even the surface directly. The composition also matters. A planet with an atmosphere rich in nitrogen and oxygen, like Earth, is particularly susceptible to nitrogen oxide production. A planet with a different atmospheric composition, say one dominated by carbon dioxide like Venus, would experience different chemistry. The specific reactions would differ, and the consequences for any protective layers in the atmosphere would vary. The fifth variable is whether the planet has a magnetic field. A strong planetary magnetic field, like Earth's, provides some protection against charged particles. But here's an important distinction. Gamma rays are not charged particles. They're photons. They're electromagnetic radiation. A magnetic field does not deflect or block gamma rays. The gamma ray flash itself passes through a magnetic field as though it weren't there. However, a gamma ray burst also produces charged particles as a secondary effect. The relativistic jet contains electrons, positrons, and protons moving at nearly the speed of light. These charged particles arrive after the initial gamma ray flash, sometimes hours or days later, because they travel slightly slower than light or take different paths through interstellar magnetic fields. A strong planetary magnetic field can deflect many of these secondary charged particles, reducing the additional ionization they would cause. So a magnetic field helps, but only partially, and not against the primary gamma ray assault itself. There is one more factor worth mentioning, and it often gets overlooked. The burst doesn't just produce gamma rays. The initial flash is dominated by gamma radiation, but the afterglow emits radiation across the entire electromagnetic spectrum, including X-rays and ultraviolet light. These lower energy but still highly ionizing forms of radiation arrive alongside and after the gamma rays. They contribute additional energy to the atmospheric disruption. X-rays in particular can penetrate deep into the atmosphere and cause significant additional ionization. The afterglow can last for hours, days, or even weeks, continuing to bathe the planet in elevated radiation long after the initial gamma ray flash has ended. So the total radiation dose isn't just what arrives in the first few seconds. It's the cumulative effect of the initial burst plus the extended afterglow. For a nearby burst, this prolonged exposure means the atmosphere is subjected to a sustained assault, not just a single flash. Let me try to bring all of this together with a concrete scenario. Imagine a planet very similar to Earth. It orbits a sun-like star. It has a nitrogen-oxygen atmosphere of similar thickness and composition. It has an ozone layer that protects its surface from ultraviolet radiation. It has a magnetic field. It has liquid water and life. Now, imagine a gamma ray burst occurs at roughly 100 light years away, and the jet is aimed directly at this planet. The burst lasts about 20 seconds. The gamma rays arrive at the speed of light. There has been no warning. The entire hemisphere facing the burst is bathed in an intense pulse of gamma radiation. In those 20 seconds, the gamma ray photons plow into the atmosphere, and the cascade of ionization begins. Nitrogen and oxygen molecules are shattered by the trillions. Free nitrogen atoms combine with oxygen to form nitric oxide and nitrogen dioxide. Within minutes, The stratosphere over the illuminated hemisphere contains nitrogen oxide concentrations many times higher than normal. These nitrogen oxides immediately begin attacking the ozone layer. Within hours, significant ozone depletion is already measurable. Within days, the ozone over the illuminated hemisphere has been reduced by 30 to 50% or more, depending on the exact energy of the burst. Within weeks to months, atmospheric circulation has spread the nitrogen oxides around the globe. The entire planet's ozone layer is now significantly depleted. Meanwhile, a brownish haze of nitrogen dioxide has formed in the upper atmosphere, dimming the sunlight reaching the surface and beginning to cool the climate. The burst itself is long over. It lasted 20 seconds, but the damage it set in motion will persist for years. The ozone layer will remain depleted for 5 to 10 years as the nitrogen oxides continue their catalytic destruction. During that entire period, the planet's surface is exposed to sharply elevated ultraviolet radiation from its host star. The UVB reaching the ground might be double or triple normal levels. UVC, which normally never reaches the surface, may begin penetrating to ground level in significant amounts for the first time in the planet's history. This is not a brief flash of danger. This is a years-long alteration of the planet's atmospheric chemistry. The planet's atmosphere has been reprogrammed. Its protective systems have been dismantled by a pulse of energy that lasted less than half a minute. And now the planet's surface, its oceans, its land, its living things must endure the consequences of that reprogramming for years, fully exposed to radiation that the atmosphere had specifically evolved to block. The atmosphere still looks the same, the sky is still there, the air still feels the same to breathe, but something fundamental has changed in its chemistry. Something invisible, something deadly, and the planet has no mechanism to fix it quickly. It can only wait as slow chemical processes gradually restore what was lost. What that prolonged exposure means for anything living on the surface is where the story takes its darkest turn. So the atmosphere has been rewritten. The ozone layer, that thin, invisible shield that took millions of years to build, has been shredded by a pulse of energy lasting less than a minute. Nitrogen oxides are circulating through the stratosphere, catalytically devouring ozone molecules by the trillions, and they will continue doing so for years. A brownish haze of nitrogen dioxide is dimming the sunlight, and now the planet's surface lies exposed to the full intensity of its host star's ultraviolet radiation in a way it hasn't been for perhaps hundreds of millions of years. But what does that actually mean for anything living down there? What happens to the creatures, the ecosystems, the interconnected web of life that depends on stable atmospheric conditions? This is where we bring the consequences down from the stratosphere to the ground. And the reality is grimmer than most people imagine. Let's start with the immediate effects. What happens during the burst itself? The gamma ray flash lasts seconds to minutes. Most of the gamma radiation is absorbed high in the atmosphere, in the stratosphere and above. That's where the ionization happens, where the nitrogen oxides are created. But not all of it is absorbed up there. Some of the highest energy gamma ray photons, and especially the secondary radiation they produce, can penetrate deeper into the atmosphere. X-rays generated by the interaction of gamma rays with atmospheric molecules can reach the lower atmosphere and, in the case of a sufficiently close and powerful burst, some of this secondary radiation can reach the surface itself. For a burst at a moderate distance, say a few hundred light years away, The direct radiation dose at the surface during the burst itself would likely be modest. The atmosphere is a thick shield. Even with a depleted ozone layer, the sheer mass of air above you absorbs most of the high-energy radiation before it reaches the ground. A person standing on the surface during the burst probably wouldn't feel anything unusual. There would be no flash of light in the visible spectrum, no sound, no heat, no sensation at all. Gamma rays are invisible. You can't see them, hear them, or feel them. The burst would pass through the atmosphere in seconds, and on the ground, nobody would know it happened. Not immediately anyway, but for a burst at very close range within a few tens of light years, the story changes. At that distance, the radiation flux is intense enough that a significant dose of ionizing radiation could reach the surface even through the atmosphere. How significant? Studies have estimated that a powerful gamma ray burst occurring within about 30 light years could deliver a radiation dose at the surface equivalent to several times the lethal dose for humans. That's during the burst itself, in just a few seconds. You wouldn't have time to react. You wouldn't know it was happening, but the radiation would be tearing through your cells, ionizing molecules in your DNA, disrupting the chemical machinery that keeps you alive. Organisms on the surface exposed to the sky would receive the full dose. Organisms underground, underwater, or inside structures would be partially or fully shielded, depending on how much material stood between them and the sky. The radiation would hit like an invisible wave, passing through the atmosphere and depositing its energy in anything it encountered. But here's the crucial point. Even if the direct radiation dose during the burst is survivable, even if most organisms on the surface make it through those initial seconds without lethal damage, the real catastrophe hasn't begun yet. The real catastrophe is what comes after. It's the slow, grinding, years-long assault that follows the initial flash. Because once the ozone layer is gone, the planet's host star becomes the weapon. Every star emits ultraviolet radiation. Our sun certainly does. Under normal conditions, the ozone layer absorbs the most dangerous wavelengths, UVB and UVC, before they reach the ground. What gets through is a filtered, weakened version of the sun's ultraviolet output. Your skin can handle some of it. Plants can handle some of it. Ocean life can handle some of it. Everything alive on the surface has evolved to cope with the normal levels of ultraviolet that make it through the ozone layer. But with the ozone layer severely depleted or effectively destroyed, the filtering stops. The full spectrum of ultraviolet radiation from the star now reaches the surface without significant absorption. UVB levels could double, triple, or increase by a factor of 10 or more, depending on the severity of the ozone depletion. And UVC, which under normal conditions never reaches the ground at all, begins arriving at the surface in biologically significant quantities. UVC radiation is extraordinarily damaging to biological molecules. It's absorbed very efficiently by DNA, and when DNA absorbs UVC, the photon's energy causes adjacent thymine bases in the DNA strand to bond together, forming what are called pyrimidine dimers. These dimers distort the shape of the DNA double helix. They prevent the cell's molecular machinery from reading the genetic code correctly. Cells have repair mechanisms that can fix some of this damage. There are enzymes that cut out the damaged section and replace it with the correct sequence. But these repair mechanisms have limits. If the rate of damage exceeds the rate of repair, errors accumulate. Mutations pile up. Cells begin to malfunction. They die, or worse, they become cancerous, replicating out of control with corrupted instructions. Now think about what this means for an entire biosphere. Every organism exposed to the sky is being irradiated with levels of ultraviolet that its biology was never designed to withstand. Every leaf on every plant, every blade of grass, every insect crawling across an open field, every bird in the sky, every fish in the shallow waters of lakes and oceans, everything that the ultraviolet can reach is taking damage, not in a dramatic, visible way. You wouldn't see organisms bursting into flame or dissolving. You see something quieter and in many ways more terrible, a slow sickening. Plants developing lesions on their leaves, their photosynthetic capacity declining, animals developing cataracts, skin damage, immune suppression, reproduction rates dropping as genetic damage accumulates in reproductive cells, populations thinning as mortality increases and birth rates fall. Let's talk about photosynthesis, because this is where the cascade really begins. Photosynthesis is the foundation of nearly all life on Earth. It's the process by which plants, algae, and certain bacteria convert sunlight, carbon dioxide, and water into organic matter and oxygen. Almost everything alive on this planet depends on photosynthesis, either directly or indirectly. You eat plants, or you eat animals that eat plants, or you eat animals that eat animals that eat plants. Trace any food chain back far enough, and you arrive at a photosynthetic organism capturing energy from sunlight. Photosynthesis is the base of the pyramid, the engine that drives the entire biosphere. Photosynthetic organisms are particularly vulnerable to ultraviolet radiation. The molecular machinery of photosynthesis, the chlorophyll molecules, the protein complexes, the membranes in which they sit, is sensitive to UV damage. Under normal conditions, photosynthetic organisms have various protective mechanisms. Some produce pigments that act as sunscreens, absorbing ultraviolet light before it can reach the sensitive machinery. Some have DNA repair systems that fix UV damage. Some can move or reorient to reduce their exposure. But these mechanisms evolved to handle normal levels of ultraviolet, the levels that exist under an intact ozone layer. When UV levels suddenly double or triple or increase tenfold, these protective mechanisms are overwhelmed. The damage outpaces the repair. On land, plants would begin to suffer. Leaves are the primary organs of photosynthesis, and they're directly exposed to the sky. Elevated ultraviolet radiation damages the photosynthetic pigments in leaves, reducing their ability to capture light energy. It damages the DNA in leaf cells, causing mutations and cell death. Over time, leaves develop necrotic spots, brown patches where cells have died. The plant's ability to produce food through photosynthesis declines, growth slows, seeds become less viable as UV damage affects the reproductive cells. Forests, grasslands, and croplands would all feel the effects, though the severity would vary depending on the species and the degree of ozone depletion. Some plants would cope better than others. Plants in environments that already receive high levels of ultraviolet, such as alpine environments or equatorial regions, tend to have better UV protection. They produce more protective pigments. Their DNA repair mechanisms are more robust. These species might survive with reduced growth, but without catastrophic die-off. Other species, particularly those adapted to shade or to regions with lower UV levels, would be far more vulnerable. The ecological composition of plant communities would shift as UV-resistant species gained an advantage and UV-sensitive species declined. This kind of shift in plant communities would cascade through the entire terrestrial ecosystem, affecting every organism that depends on plants for food or habitat. But the terrestrial effects, as serious as they are, might not be the worst part. The worst part might be what happens in the oceans, because the oceans are where the real foundation of Earth's biosphere lies, and they are terrifyingly vulnerable to ultraviolet radiation. The base of the oceanic food chain is phytoplankton. These are microscopic photosynthetic organisms, single-celled algae and cyanobacteria that float in the upper layers of the ocean, the photic zone where sunlight penetrates. Phytoplankton are small, often just a few thousandths of a millimeter across. They're individually insignificant, but collectively, they are among the most important organisms on the planet. Phytoplankton produce roughly half of all the oxygen in Earth's atmosphere. Every second breath you take comes from oxygen generated by phytoplankton. They also absorb enormous quantities of carbon dioxide, playing a critical role in regulating the planet's climate. And they form the base of the marine food web. Zooplankton eat phytoplankton. Small fish eat zooplankton. Larger fish eat smaller fish. Marine mammals and seabirds eat the larger fish. Remove the phytoplankton, and the entire marine food web collapses from the bottom up. Phytoplankton live in the upper few tens of meters of the ocean, because that's where sunlight is strong enough for photosynthesis. But this is also the zone most exposed to ultraviolet radiation. Under normal conditions, phytoplankton can tolerate the UV levels that penetrate the ocean surface. Though UV is one of the stresses they face, many species produce UV-absorbing compounds called mycosporin-like amino acids that act as natural sunscreens. Others can migrate vertically in the water column, moving deeper during the day to avoid the strongest UV and rising to the surface at night or when UV levels are lower. But a massive increase in surface UV, the kind that would result from severe ozone depletion, would overwhelm these defenses. Studies have shown that significant increases in UVB radiation reduce phytoplankton productivity measurably. Experiments exposing phytoplankton to elevated UV levels have demonstrated reduced growth rates, decreased photosynthetic efficiency, and increased mortality. And these experiments typically involved UV increases far less severe than what a nearby gamma-ray burst would produce. With the ozone layer severely depleted, the surface ocean would be bathed in UV levels that phytoplankton have never experienced in their evolutionary history. The most sensitive species would die first. Their populations would crash within weeks or months. More resistant species would survive longer but with reduced productivity. Overall phytoplankton biomass could decline by 30%, 50%, or even more, depending on the severity and duration of the ozone depletion. Some models of gamma-ray burst effects on ocean ecosystems have estimated that a close burst could reduce global phytoplankton productivity by as much as 90% during the peak of the ozone depletion. The consequences would ripple upward through the food web. Zooplankton populations, deprived of their primary food source, would crash. Small fish that feed on zooplankton would starve. Larger fish, marine mammals, seabirds, all would feel the effects. The ocean, which currently teems with life from surface to floor, would become quieter, emptier. Not lifeless, because life is remarkably resilient and some organisms would survive in deeper waters or in environments with natural UV shielding. But the ocean's productivity, its ability to support large populations of complex organisms, would be dramatically reduced. There's another dimension to the phytoplankton die-off that most people don't consider. Phytoplankton don't just produce oxygen and food. When they die in large numbers, Their decomposition consumes oxygen. Bacteria that break down dead organic matter use dissolved oxygen in the water. A massive die-off of phytoplankton would create a surge of dead organic material sinking through the water column. The bacterial decomposition of this material would create dead zones, regions of the ocean where dissolved oxygen drops so low that most marine life cannot survive. We already see this effect in modern oceans where nutrient pollution causes algal blooms that die and decompose, creating hypoxic or anoxic zones. A gamma-ray burst-induced phytoplankton die-off would be this process on a planetary scale. Large regions of the ocean could become oxygen depleted, adding another layer of stress to marine ecosystems already reeling from the loss of their primary producers. And it gets worse still. With phytoplankton production drastically reduced, the biological pump that normally removes carbon dioxide from the atmosphere and transports it to the deep ocean would slow down or shut down. Phytoplankton absorb carbon dioxide during photosynthesis. When they die, some of that carbon sinks to the deep ocean in the form of dead organisms and fecal matter, effectively sequestering carbon away from the atmosphere for centuries or millennia. If phytoplankton populations crash, this carbon pump stops working. Carbon dioxide that would normally be absorbed by the ocean stays in the atmosphere instead. Over time, this could lead to a buildup of atmospheric carbon dioxide, potentially warming the planet through an enhanced greenhouse effect. But wait, didn't we say earlier that the nitrogen dioxide haze would cool the planet by blocking sunlight? Yes. And this is where the climate effects become genuinely complex and difficult to predict. You have competing forces acting simultaneously. On one hand, the nitrogen dioxide haze blocks visible sunlight, reducing the energy reaching the surface and cooling the planet. On the other hand, the collapse of the biological carbon pump allows carbon dioxide to accumulate in the atmosphere, which would tend to warm the planet through the greenhouse effect. On a third hand, if you want to stretch the metaphor, the cooling itself could trigger the expansion of ice and snow cover, which increases the planet's reflectivity, bouncing more sunlight back into space and amplifying the cooling. The net effect on climate would depend on the balance of these competing factors, and that balance would shift over time as the haze cleared and the ozone layer slowly recovered. The most likely scenario, based on the modelling that's been done, is an initial period of cooling lasting several years, driven by the nitrogen dioxide haze, followed by a gradual warming as the haze clears, but the ozone layer remains depleted. The cooling could trigger agricultural failures, crop losses, and famine for any civilization that depends on agriculture. Even modest cooling of a few degrees can dramatically reduce crop yields, shorten growing seasons, and shift precipitation patterns. Civilizations have been destabilized by far less severe climate disruptions throughout human history. Let me paint the full picture now. Because the cumulative effect of all these things happening simultaneously is worse than any of them individually. Imagine an Earth-like planet hit by a gamma ray, burst close enough to deplete the ozone layer by 60 or 70%. In the months and years that follow, here is what that planet experiences. Ultraviolet radiation at the surface is 2 to 5 times normal, with UVC reaching the ground for the first time. Sunlight is dimmed by a nitrogen dioxide haze, reducing temperatures at the surface. Terrestrial plants are stressed, with many species showing reduced growth, leaf damage, and declining reproductive success. Agricultural crops, if any exist, are failing due to a combination of increased UV damage and reduced sunlight. Phytoplankton in the oceans are dying in enormous numbers. The marine food web is collapsing from the bottom up. Dead zones are forming in the oceans as decomposing phytoplankton consume dissolved oxygen. The atmospheric carbon cycle is disrupted as the ocean's biological pump slows. Land animals, including any intelligent beings, are experiencing increased rates of skin cancer, cataracts, and immune suppression. Amphibians, which have particularly UV-sensitive eggs and skin, are especially hard hit. Amphibian eggs are typically laid in shallow water or on moist surfaces, completely exposed to sunlight and therefore to ultraviolet radiation. Under normal UV levels, amphibian embryos develop successfully. Under elevated UV levels, studies have shown dramatic increases in embryo mortality and developmental deformities. An entire class of animals could face near total reproductive failure across large parts of the planet. Insects that pollinate plants and form the base of terrestrial food chains are declining. The entire biosphere is under simultaneous assault from multiple directions, all stemming from a single event that lasted less than a minute. And here's the thing that makes this so different from other catastrophic scenarios. This planet hasn't been hit by anything. Nothing has crashed into it. There is no crater, no fireball, no tsunami, no mushroom cloud. The planet looks the same from space. The oceans are still blue. The continents are still green, at least at first. The atmosphere is still there. The planet hasn't been blown apart or scorched or physically damaged in any obvious way. If you flew past it in a spacecraft, you might not notice anything wrong at all. The destruction is invisible. It's chemical, biological, ecological. It's happening at the molecular level, in the stratosphere, in the DNA of living organisms, in the chemistry of the ocean. The planet is dying, but it's dying quietly, slowly, from the inside out. And that, in many ways, is the most terrifying aspect of what a gamma-ray burst does to a world. It doesn't destroy the planet, it poisons it. This needs to be stated clearly because popular culture has created a very specific image of what cosmic destruction looks like. In movies and television, when a planet is threatened by a space catastrophe, the planet usually explodes. There's a dramatic fireball, a shockwave, debris flying everywhere. The Death Star blows up Alderaan, and the whole planet shatters into pieces. An asteroid hits, and the surface is consumed by fire. These images are cinematic and dramatic, but they have almost nothing to do with what a gamma-ray burst would actually do. A gamma-ray burst at any plausible distance that would affect life does not blow up a planet. The total energy delivered to the planet, while enormous by biological standards, is negligible compared to the gravitational binding energy that holds the planet together. Earth's gravitational binding energy, the amount of energy you'd need to completely disassemble the planet and scatter its material to infinity, is about 2.24 times 10 to the 32 joules. Even the most powerful gamma-ray burst at a distance of a few light years would deliver only a tiny fraction of that energy to the planet. The planet would remain completely intact physically. Its mass, its gravity, its rotation, its orbit, all unchanged. The oceans would still be there, the mountains would still stand, the atmosphere would still cling to the surface, nothing would look different from a distance. But life on the surface would be in crisis, because life doesn't depend on the planet remaining physically intact. Life depends on chemistry. It depends on the delicate balance of atmospheric gases, the stability of the ozone layer, the predictability of the climate, the integrity of DNA molecules, the productivity of photosynthetic organisms. These are genuinely fragile things. They can be disrupted without any physical destruction at all. You don't need to shatter a planet to devastate its biosphere. You just need to change its chemistry. Consider an analogy. Think of a greenhouse where rare tropical plants are growing. The greenhouse is sturdy. The glass walls and roof protect the plants from the cold outside air. If you threw a rock at the greenhouse, you might break a window. That would be dramatic and visible. But imagine instead that someone quietly replaced the air inside the greenhouse with a slightly different gas mixture, one that was subtly toxic to the plants. From outside, the greenhouse would look exactly the same. The glass would be intact, the lights would still be on, but inside, the plants would be wilting, yellowing, dying. That's what a gamma ray burst does to a planet. It doesn't break the glass, it changes the air. The timescales involved make this especially devastating. If the ozone layer were depleted for a day or a week, most ecosystems would recover. Life is resilient. Organisms can repair DNA damage. Populations can bounce back from temporary stress. But the ozone depletion from a gamma ray burst doesn't last a day or a week. It lasts years, 5 years, 10 years, maybe longer for a particularly severe event. That's long enough for populations to crash, for species to go extinct, for food webs to unravel, for ecosystems to reorganize into fundamentally different configurations. 5 to 10 years of elevated ultraviolet radiation is not a temporary disruption. It's a sustained environmental shift that pushes ecosystems past their ability to cope. Marine organisms that live more than a few meters below the ocean surface would be relatively protected from the direct UV effects, because water absorbs ultraviolet radiation fairly efficiently. Below about 10 meters, UVB intensity drops significantly. Below about 70 meters, very little ultraviolet penetrates. This means that deep-sea organisms, creatures living in the abyssal plains, around hydrothermal vents, in the deep trenches, would be largely unaffected by the UV increase. They don't depend on sunlight for energy. They don't need the ozone layer. Their food sources are either chemosynthetic, deriving energy from chemical reactions rather than sunlight, or they feed on organic material that sinks from above. In the short term, the rain of dead phytoplankton sinking from the surface might actually provide a temporary boom in food supply for deep-sea scavengers. Similarly, organisms living underground, in caves, in deep soil, or under thick layers of rock would be shielded from the radiation. Microbes that live in the subsurface, which constitute a surprisingly large fraction of Earth's total biomass, would be essentially unaffected by a gamma ray burst. Life in these protected environments would persist even through a severe event. And this is an important point. A gamma ray burst, even a close and powerful one, would probably not sterilize a planet entirely. It would devastate the surface biosphere. It would cause mass extinctions among surface-dwelling organisms. It would collapse marine food webs. It would disrupt the climate, but it would not kill everything. Life in the deep ocean, life underground, life in protected environments, these would survive. The planet's biosphere would be badly damaged, but not completely erased. Given enough time, probably millions of years, life would recover. New species would evolve to fill the ecological niches left empty by the extinctions. The ozone layer would rebuild. The climate would stabilize. The planet would eventually return to something resembling its pre-burst state. though with a very different cast of characters. But for the civilizations and complex ecosystems living on the surface at the time of the birth,